I'm John Hodgson. I'm a chief architect for APM for Riverbed. And today we thought we'd have a little bit of fun and do a little bit of a more thought leadership talk, more of like a TED talk than a marketing pitch. It'll be a little bit about Riverbed in the beginning, but the vast majority is going to be stuff you could take home and use for your performance management practice and really any data analysis that you do. So I've been working with performance analysis for at Riverbed for about 15 years now. And before that, some related practices. And there's some things I've learned along the way of cases where sort of data has not added up or it's lied to me. And these themes keep recurring, so I wanted to teach you these principles that are kind of widely known in other industries, and hopefully you could take that back to your day-to-day practices when you get back to your day-to-day jobs. So to provide context, just a little bit about what we do at Riverbed. We are the digital performance company, and what we monitor are end-user experience interactions with mission-critical applications, and we do that through the depths of that application. So we don't just do EUE, but go through the network, through the routers and switches and the various containers and VMs and so on. And we follow every end-user transaction in detail down to the packet, code, SQL level. So we take this big data approach where instead of aggregating sort of rough averages of what people are doing, if John Smith logged in at 12:55, 05 and 43 milliseconds, we know that. And we know what tiers they hopped across and so on. So our background and what I've been doing, again, for 15 years is doing this end-to-end monitoring from the end-user device down through the applications with your traditional APM, your code tracing, and then on the network in between, the NPM data, which is, again, all packets for each transaction all the time. And we combine that and we call that Steel Central. So that is our unified APM performance management platform, which is a big data, all transactions, all the time, across all these tiers, all stitched together, so that we can, A, know that your customers are happy, know that every customer is happy with everything they're doing, not on average, and then know precisely what they touched, and if there's an issue, narrow it down to something actionable that you can solve. And since I've had access to this really rich data set for so long, as I mentioned, I keep seeing cases where customers will bring me problems that they've had that they want to use our tools on, and what they tell me doesn't add up when I put my instrumentation on. I often say, like, why do you think you're seeing what you're seeing? And that's what this session is about. So the themes today are going to be this. Edgar Allan Poe said, "Believe nothing you hear and only half that you see." And this is about trusting your data, trust but verify. I want to make sure we don't implicitly trust data that may be wrong. And then secondly, a key principle to open your mind today from Weird Al. This is a song I like, but basically we find too many cases, and I've seen too many cases where people are confident based on the data that they've provided. It is a fact because their monitoring tool said something is a certain way, and then they go chasing an issue that either didn't exist or didn't exist in the way that they thought it did. So we want to take a step back and say, let's take a different approach to this, okay? So I want to start with a real-world case in the actual performance management space, and then we're going to switch gears to some analogs in other industries. So I had a customer, and this is actually one of the cases that inspired me to do this talk, and they had been, without us, monitoring an application in the cloud using the cloud-native tools that came from the vendors. And so 1 minute granularity, and their application in a certain version was showing this CPU load. And they modified the app, they rolled out a new release, and CPU went up to 61%. And they came to me because they could not quite understand what caused such a major jump in resource utilization. So what I'm going to do throughout this session is we're going to do some quizzes. And if you've never done Mentimeter before, it's really easy. I'll ask you to take out your phones. It'll be a little fun, I promise you. And just go to menti.com, enter that code 24435. And I just want to ask some simple questions. It's going to be anonymous. Nobody's going to get anything, get embarrassed if they're wrong. And but I want to make you think and analyze the data. So simple question, which is, how much did CPU load increase by based on what you see? Start at 7, we revised the app, and it went to 61. Has anyone voted? It doesn't look like it's refreshing. It says 24435. It's a little blurry. There we go. So menti.com. Okay. So we'll wait till we get a handful more, since this is the first time we'll do them. We'll do it quicker in the remaining ones. I think we've got, I don't know, probably about 50 so people in the room. So we got a battle between 95% and 54%. So we're going to see who wins. So we got people who are literally doing the math of what they see, and then another team who believes that it's even worse than this is purporting it to be. We're going to give a couple more minutes for new answers. Let's get to 25. And then for those of you who haven't done it, we've got more questions coming. Oh, we got a 5%. Someone who doesn't believe that. Anybody else? They're the outlier. All right, one more and we could be done. That at least about half the room did it. Okay, so what is the answer? The answer is 5%. And that's what this whole session's about, is data that makes you so confident in your answer, yet you were wrong. The reason it's 5% is that if we look at the raw data under the covers in 1 second granularity, which is the blue, that is the pattern of what was actually happening with that application. So this application, every minute, at the beginning of the minute, did some amount of processing that took about 15 seconds. And the cloud monitoring tool, which was sampling once a minute, synchronized with that, was catching it right after the spike. When they made the rev of their app, it made those spikes slightly wider by 1 or 2 seconds. And then the sampling point now was catching on the middle of the spikes instead of at the bottom. Neither answer was right, by the way, from the red lines. It wasn't 7, nor was it 60. It was a 5% increase, and as I said, it went from 20 to 25. So this is an example of how data that you're so confident in can lie to you. Now, this is admittedly somewhat of a unique corner case where the sampling rate perfectly synchronizes with the behavior of the application, but you'll see many, many, many examples of this. And the theme of this talk is that we're not saying that 60-second data is bad. We're saying it's bad for certain purposes. If you're trying to monitor how long it's, what is the water level in your pool as you fill it, it can only change by a certain amount every minute. 1 second, 1 minute data is great. Heck, 10-minute data would be fine for that. But if you want to measure the light level in a room where people could be snapping strobe flashes, we can go from totally dark to totally light in a room in the blink of an eye. In that case, 1 minute data is not going to be enough to get an accurate reading of that. Okay, so let's do one more quiz now. A different scenario. Let me advance so you can do it. So I want you to describe, based on the data you're seeing, how is CPU changing over time. So it's a 15-minute window, just like before. We have a 0 to 100 CPU load scale, and just pick what you think it's doing in Menti. We'll do this a couple more times. I won't react because I don't want to skew your choices. Oh, it's neck and neck. People who are literal and people who are already seeing through me, which is wonderful. And then someone who's going to deviate from the rest. All right, we'll get to 25. If you want to keep voting while I'm talking, that would be great. I am very curious to see, but you're going to get the answer pretty soon. All right. Who else is waiting? All right, well, we'll stick around 25. That's good. Okay. So what is the answer? The answer is it actually doesn't change at all. And if we look at the data behind the scenes, it is effectively the exact same data we saw in the previous example, with one subtle difference. Instead of these spikes happening every 60 seconds, they are now happening every 61 seconds. And that very slight offset is causing the sampling point to occur at different points along the spike. So every single one of these answers is completely wrong. This is very common. So what this would be an app that does a certain amount of processing and waits a fixed amount of time and then does a certain amount of processing. So when that amount changes, the delta between the spikes increases, and then you'll see these massive skews in your reported data. Okay. Why this is happening, now we're going to switch to the theory, is a concept called aliasing. So aliasing are artifacts and distortions that can occur when you try to sample something, a signal like a sine wave, into something digital that has discrete samples. And this is a fundamental principle of the Nyquist-Shannon theorem, which is used, it is the foundation of digital signal processing, which basically establishes the conditions you need to say, how do I capture a signal in fidelity so that it matches the original? So how do I take a picture with a digital camera so that it looks like what I saw? Right? How do I record a video where it represents what I saw? How do I record audio where it sounds like what was played? That is a very key cornerstone of this. And the particular law that we will deal with is the Nyquist rate. So the Nyquist rate is the minimum rate of sampling you can use to accurately sample a signal without introducing errors. And if you go below this, you will get into aliasing. And this is, when it comes to pure signal processing, sine waves and so on, the rule is twice the highest frequency. So human hearing could go up to about 20 kilohertz, and that's why CDs are sampled at 44.1, because it's double that plus a little bit for some other reasons. And because if you sampled at 20, you would only be able to have frequencies up to 10 kilohertz. And if you don't do that, you have aliasing that occurs. So this is a fundamental concept in digital signal processing that we largely ignore or unaware of or don't try to apply to performance management data. And that includes the vendors who are providing that data. And this is something I was unaware of 15 years ago when I started in this field, but then being exposed to this 1-second data, this big data approach, I started realizing like there's cases where the data is not adding up, and that's where I started learning like this has exact applicability just like it does in every other field. So this is your textbook example of Nyquist. Here we have a 60-second period, so each sine wave, the initial part from 0 to 0 is 60 seconds. And to sample it, I need to sample it 30 seconds. That's how I can accurately reproduce this. And an aside is that this will let you accurately determine the frequency of the signal, but if you want to measure the amplitude accurately, you actually have to have even more granularity. Because if I offset these samples just a bit, it would catch the sort of sine at almost the tip, and it wouldn't be quite as high. So our world of performance management, we're not dealing with perfect sine waves, we're dealing with things like intermittent spikes of response time, intermittent spikes of CPU. And what you'll find is that this high definition data and this high resolution data is really critical in order to not only detect the spikes, but quantify them accurately. So the blue is the source signal, the red is the sampled result. And what I want to show you is what happens when I make slight changes to the sampling interval. At 45 seconds, it starts degrading. At 59, right, the 6-second sample, I get this weird, increasing amplitude over time, does not reflect what you're seeing. And at 60 seconds, we get a beautiful flat line, which suggests nothing's happening. Now, of course, if I offset the sampling, it could ride that wave all the way up to the top or all the way down to the bottom, which means this sampling at 60-second signal at 60-second sampling could give you an answer anywhere between plus 100 and negative 100, just depending on where you happen to accidentally sample it. And this is actually a problem that happens again in that first example. It's just, it was luck of the draw, where did I hit the spike? And this happens. So let's keep going. 61 seconds, 65, 75. We've got a new sine wave at 90, but it's not the right sine wave. At 100, it gets wider. At 105, it gets even wider. At 112, it's a very wide one. We can't see the rest of it. At 116, it's only the beginning of it. And it's flat again at 120 at your multiples. 124, 128, 140. So the point is that here we have the truth being that blue signal in every one of these examples, and depending on how you sampled it, you got it wrong. There was only one way that got it right, was when we abided by the Nyquist rate, and we did at half the frequency. So how that translates in our world, again, if you have, for example, you're trying to capture a 10-second increase in response time, you need to have at least 5-second granular data to catch it accurately. And if you want to quantify it accurately, you probably need to go into the 3 or 2 or even 1 second resolution. Okay? So hopefully you're taking away this sort of now critical eye that maybe I have to be careful about trusting the data that I'm getting from my performance monitoring. This concept of aliasing is everywhere in the world, right? We have a digital world now where we're taking the analog constructs of our world, images, sound, video, data, and we're digitizing it. And every practice that takes that analog data and tries to capture it and store it in a digital manner suffers from and has to deal with these issues. Yet again, in the performance management world, we probably don't see that much. And again, don't be embarrassed because I'm having this talk because I'm not seeing this a lot. Show of hands, how many people have ever considered before aliasing being a factor in their monitoring data? Right? So I'd say maybe about less than a quarter of the room, and I'm not surprised by that. And for those of you, maybe you're probably electrical engineering majors and that was something you were brought up with, but others just don't even think about it. So now we're going to take you through some corollary examples in the world of every day, and this is why we called it the sound of performance data, is that I wanted to show examples of aliasing every day and why, if all of these other industries that we respect and we rely on have taken this to heart and really are embracing these scientific principles, why has our monitoring practices, our statistics and reporting and so on hasn't done the same? Audio is actually one of the tougher ones to replicate. I have two audio examples and a bunch of others. Because also your ear will have to be able to hear the distortion, but hopefully we'll catch it. So this is a properly sampled sawtooth signal, where this is relatively accurately describing that sawtooth of a tone. And when it's improperly sampled, you get aliasing and it reverses. And for those of you who monitor Java and .NET, this is a heap-free chart, right? So you see heap-free go like this. If you sample it wrong, you'll see it go in the opposite direction. If you ever see a heap-free chart, or heap usage, whichever, which doesn't have a sawtooth, but it looks like it's jumping around, it's because it's got a subsampling period sawtooth. So even in my 1 second data, I sometimes see heap usage charts which don't even have a sawtooth because it's cycling through the whole heap on a sub-second basis. So this example, while it's audio, actually applies perfectly directly to what we're doing in APM. So I'm going to play some tones. I want you to listen. We're going to interleave between the proper tone and the aliased one, which sounds kind of gritty and distorted. So it's that grittiness, which is what is aliasing. Now, normally when you downsample, you've got to get rid of some frequencies. You can do that in a clean way where the sound sounds sort of flatter or rounder, but it doesn't have that distortion, that noise. Okay? Here's an example with a song. Jonathan Colton, for whoever's developers, if you've never heard the song Code Monkey, it's hilarious. I love it. I'm just going to change the sample rate and you'll hear how it degrades. It sounds like it came from the 80s right now. So had I done that properly, the sound would have lost some of its higher frequencies, but it wouldn't have got that distortion sound. It wouldn't have sounded like a grunge band. Okay? And that's aliasing in audio. And it turns out, because when I came up with this concept and I named this, I wanted to show a lot of examples with audio. It is very hard to recreate these examples because just about every audio tool in existence, even the free, cheap ones written by kids, they don't allow you to resample in a wrong way. They automatically apply what's called a low-pass filter, which filters out the frequencies that would have caused aliasing, and that basically just about every tool resamples properly. And it was very hard for me to resample improperly for this example. Okay, video. So here's aliasing examples in the video space. I want you to look at this video and imagine if this is all you had to go by, how would you interpret what you're seeing? And don't try to apply what you think you know about from movies and so on. How would you describe, if you had to write an article about this for the newspaper, over this amazingly mysterious video that you just witnessed someone shared with you, right? But think about this, right? If this was your performance data that was showing you this image and you had no reason to disbelieve it, you would go off on a completely wrong tangent. This is what I call performance phantoms. I have another talk I did a couple years ago. If you look for me on YouTube, I'll share a link at the end. Performance phantoms are these things that either look like problems but are not at all or not quite what you think they are, or you've skipped over what it really is and are on the track of something else. You waste lots of time trying to optimize or fix issues that are the wrong issues or non-existent issues. And it's issues like this that cause it, okay? Text is one of the earliest things that we've probably, as computer people, came in contact with regard to aliasing. And in fact, the term comes up quite a bit. So in text, right, we have an analog letter here, effectively, straight lines and nice smooth curves. And when we create a digital copy of that, we grid it, we do the nearest neighbor matching, and that's what creates the pixelated version of the letter. So back in our earliest days when we got out of, when we started getting into CGA and all that, where we actually had graphics and fonts, this is what type looked like. And we called that the jaggies because they weren't smooth. And as resolution decreases, the effects of this aliasing becomes more evident, right? So on the left, it's very smooth, and then it gets more and more and more granulated, okay? So in the print world, they apply something called anti-aliasing for text, which is this sort of interpolation of the edges. And it tries to smooth things out, make it feel not quite as jagged. But even in the most extreme examples, it's still quite obvious that this is happening. And the point being is you can try to combat aliasing with clever algorithms and so on. And they have different variants of that for audio, for video, and so on. But at the end of the day, you can't make something out of nothing. And in our world with performance management, like there really isn't a corollary concept. You just have to capture right. And if you know you can't capture a certain type of event, you have to not trust the data that you have and just discard it. Find another way to do it. So let's have a survey. Let's bring out that Menti one more time. And for everybody who said I don't trust this data, thank you. So what character do you see? And if you're going to be really honest, you should do it based on what you see, not based on what you think it is based on the rest of the class, rest of the session, but, that's okay. I'll take either way. So you guys are on to me now. Most people are realizing this is probably not a B. I actually last night thought that I might actually make it a B under the covers and say, no, it is a B this time, it wasn't aliasing. But you guys are getting the point now, right? What looks like something turns out is not. And in fact, when we had digitized that, what that wound up being was, like I said, perfectly a 13. And if we applied anti-aliasing to it, it looks like a 13. We've got that little bit of gray in the middle. But I would say if you're in the back and you probably have bad eyesight like I do and don't have your glasses, you probably think it's a B, right? So remember, you guys have the advantage of knowing that this session is about these optical illusions, right, or these aliasing illusions. If you're sitting in front of your monitoring screen and with 1 minute data, you have to be you have to be suspicious that this type of thing is happening. So photography, aliasing is pretty prevalent. We're gonna have another quiz. I may not be tricking you this time. So, simple question. Describe the shirt. What is it? See, I'm trying to trick you now, but maybe it's checkered. You don't know. Okay, so what's the right answer? The right answer is it's striped, or you should not fall for this again. So actually, funny thing here, this projector I don't think is perfect 1080p. And if you notice, there's kind of this yellow tint to this. It's not on my screen. So this projector is aliasing the slide and creating a colored artifact that's not in my source material. So we actually have an unintended aliasing that occurred here. But anyway, it is a striped shirt. It does not have yellow in it. My slides don't have it in there. When I reduce it by 25% without an anti-aliasing technique, you get this crazy psychedelic moire, is what that's called. And then when we try to combat the moire with anti-aliasing, it actually removes the stripes altogether, and we think it's a solid shirt. So if you were trying to order yourself that shirt on the right and the shirt on the left came to you, you'd probably be pretty unhappy, right? This is a problem that graphic designers have to live with. And graphic designers are well aware of this concept of moire and sort of where this thing appears, and they deal with this on a day-to-day basis. I want you guys to be just as aware of that when it comes to when you're looking at charts about CPU or disk usage or whatever it happens to be, Java response time. So color moire is exactly what happened in the previous slide. Is where you get these weird bands that pop up because of a grid. I had a 1080p slide, which I'm showing, I think, on a 720p projector, and that misalignment of the grid caused the color artifacts in the previous slide. But you see here the suit's got these weird color bandings, and so does this. So bottom line, you should walk away with, this happens all the time. It's something that the rest of the world is constantly trying to combat, yet for some reason we don't realize it in our world. Every field kind of deals with this. Weather and Doppler, mass spectrometry, microscopy, ultrasound, MRI, they all have examples of this. So in the ultrasound, I'm not an ultrasound guy, I don't really know how to read them, but apparently the colors of red to blue determine the flow of something. And because of certain aliasing techniques, it can look like blood's flowing in the wrong direction, like towards the heart instead of away in certain veins and arteries. Mass spectrometry, it'll actually misquantify things. Weather radar creates these weird blind spots. MRIs has a ghost, and the list goes on and on. So bottom line is that this is everywhere, but where it matters for us, for our worlds. We have taken this journey for media over the years where we're continually trying to improve upon quality, right? We're trying to approach fidelity. That's the goal, right? The real world is on the left, and these things that we're capturing and reproducing on the right, on the far right, would be a digital replication of that real world, right? So fidelity is key. We made the jump from analog to digital, and that's where all of these DSP and aliasing problems started to evolve. And in those first generations of products, they actually suffered a bit more than they do now because we figured out how to work that out. But all of us are striving for, we want the 4K Blu-rays or the ultra-high def TVs, 51 megapixel cameras, right? We're trying to get closer and closer and closer to the fidelity of the real world. Yet we don't make those same demands for our performance data. I'd argue that we've regressed since the 70s. In the 70s, when all you had was command line and you were tailing log files and outputs, you were probably easily getting one sample per second coming out on your command line. And we can still get that today from log files, and our log files even have millisecond or even microsecond granularity, right? But when we look at the charts, the moment they make their way into a web UI, all of a sudden, and I mean, just walk around the floor, I dare you, and look at anyone who's got charts up, you will see, for some window of time, you'll see there'll be a spike, and then a flat line for a while, then a spike. I mean, because the gaps in between, it'll be minute granular data or 5-minute data, or even 15-second data. And for some reason, we say, well, even though we're getting it 1 second under the covers, I guess because it's a cloud SaaS monitoring solution or something, we can only show it to you at 1 minute. It makes no sense to me. Because we can get 1 second telemetry from the space station live in our browsers today, right? This ISS Live, you want to go see what the space station is doing, you can get it. 1 second samples just stream by. So I'm very frustrated that, well, why is it we don't impose that same, our mission critical apps that we're spending hundreds or thousands of man hours trying to optimize and improve performance on and solve problems for teams that are doing a lot of work. And the first thing we're starting with, which our data is wrong, which means a lot of times the solutions we're making are wrong. I mean, how many people, show of hands, developers, where you have been trying to solve a problem for a long time, you keep putting fix after fix in, and you think you got it, but you only made a marginal improvement? The rest of you are lying. But that happens, right? And it's because you're chasing a phantom, and probably because the very first thing you saw, right? If my customer, I've seen cases where they look, is it CPU? The CPU chart shows flat, and they go, nope, let's look for something else. No, it was CPU, right? It was a VMware contention or a container contention. But because the data didn't reflect that, they looked for problem number 2. There was no problem number 2. They missed the first real root cause, and they'll never find it again. And they've wasted a lot of time. So I want to show you comparisons of sort of what this data looks like when we come back to the performance world. So this is based on, I have a real-world customer, financial processing company, really response time matters. And we monitor, we represent the data 1 second granularity, but I kind of recreated what it would look like at 15 seconds and so on. So they had a very precise time from an event that they got in an alerting system where they wanted to look at and say, what was going on. So they wanted to zoom into the minute. If the data was 15-second data, they would have had 4 samples. This doesn't tell you anything. At 5 seconds, you get a little bit of variance to the chart, but still doesn't tell you much. Now, 1 second, this is now all of a sudden you see that there's probably 2 things happening here. We have a little bit of a dip in the beginning, and then we have a little bit of a spike. And now all of a sudden I've got so much more richness, right? I at least have 2 periods of time I can look for. Maybe the event I was looking at came from the right. I can go see what preceded at the left. I've got 1 second precision. I can troubleshoot this even better. So when we compare these one-to-one, I mean, I think the difference is clear. You've got to have this high-def data. Now again, if I was trying to monitor percent free space on a multi-terabyte, NAS or SAN, that's cool if I have only, 1 minute samples, because how much is it going to change, right? The SAN can't go from 100% full to 100% empty, in a second, right, or in a minute. It's going to do it in chunks. But when we're trying to talk about response time or queue lengths or, connection pool size and things like that, you need to have this higher granularity data. But as much as I'm touting why 1 second data is important, let's think about it. A lot can happen in a second. I mean, how many people, show of hands, have transactions that they deal with where you're already trying to optimize for sub-second response time? Right? Almost everybody in the room, or at least 50%, right? So now we start thinking about it going, okay, well, is a second enough? Big data is the way that we now tackle this rift that's existing between sort of your time series line charts and really trying to get at the meat of really complex problems. Formula One racing is incredibly technologically advanced. They have standardized monitoring systems for the vehicles that they all use, made by McLaren. They have hundreds of live channels. They sample standard things at hundreds of times per second. And then when they detect certain issues, they can increase that to even 10,000 times per second if they want to do vibration analysis on a particular part of the car. Because they know that the course data isn't going to give them the information they need to solve the problems. Right? So now we've made this now just this order of magnitude, multi-order of magnitude jump from 1 second to now 10,000 samples per second. Big data is the way you're going to accomplish this. In application performance management, right, it's here, depending on what tools you use. We have it. And if we go back to that example where I was comparing the different time series charts, this is actually the source data I built those from. In a 1 minute period of time, I have 10,000 individual data points, 10,000 unique transactions by unique users, and hundreds of thousands I captured under the covers that I can plot and look for the subtleties in that data set. So if we look at these sort of spikes that occurred, and the one on the right is the one that precipitated the event, and then wanting to troubleshoot, we could see that there's transaction A and B, two types of transactions that are acting in unison with one another. And they came and said, well, we want to understand why transaction A is slow. I said, well, you're already asking the wrong question. The question should be, why are A and B slow together? And then if we look at the second event, I'd also argue, why are A and B both slow and fast simultaneously? Right? I can't get that sort of multidimensional analysis when I'm looking at simple line charts. And these scatter charts are giving me, again, this perfect view. Nothing sampled. This is exactly what happened under the covers. And now I can pivot it different ways. And I could say, well, let me look at this instead of color by transaction. Let me color it by instance, JVM or server. And let me try to see if I can find some commonality in these events. And when we looked at it colored by server in this case, we could see event 1 is orange because it's only the transactions coming from server 1. Event 2 is purple, only from server 2. If we look a little closer at the lines, you can see there's an oscillation between them, leading up to what appears to be server 2 got no traffic, server 1 then got slower, and then later on, server 2 got a dip of traffic, and then there was a gap of, server 1 got a dip, server 2 had a gap, and then was really slow. So what did this wind up being? Because by the way, APM tools, mine included, said there was slower code in here, and there was slower code in here, and they were ready to go optimize some methods. I said, hold on. The first event was the app server recycled. The load balancer sent everything to 1, and that's why it got slower. And then the oscillation is the load balancer trying to keep up with the discrepancy between the tiers, and for whatever reason, its algorithms trying to react to the event at first sent half the normal traffic it would have to server 1, and that's what caused the spike to server 2 afterwards. So in this 1 minute period of time, there are actually two very different events happening, and they were focusing on the symptom of the root cause which happened in the beginning. You would not have been able to have this sort of very detailed conversation about a 1 minute period of time for very complex tens of thousands of transactions unless you're using a big data approach. So I'm really encouraging you to try to say, if we're trying to solve delays in subsets of our users, I can't treat them on average. I have to understand that when certain users, when I have users who put more than X number of things in their shopping cart and they come from a certain vendor, that subset has slowness because we have to check inventory with that third-party vendor. And there's an exponential increase in the more things I call, for some reason they take exponentially slower to come back. So big data is about really targeting these user groups and transaction types that matter to the business. It's not just one example. I have tons of examples from customers that I've pulled over the years where we could see these very interesting patterns. When you see these horizontal bands happening at 15 seconds, 30 seconds, 60 seconds, these are human-imposed timeouts. That's what this is all about, right? When we see vertical spikes after gaps, it's, floodgates are opening and we get this burst of traffic. we get these diagonals in one direction or the other. That's queuing either on the client side or on the server side. And we even get these weird sort of multi-dimensional problems where it's like, okay, why is it both fast and slow? Or why is there a ramp and then a sub-ramp underneath? If a system is scaling properly, it should look organic. It should look random. To use a mathematics term, stochastic, right? When you see artificial edges to things, lines and patterns and so on, these are throttles, they're constraints and limits that are being applied. And this is the stuff that you have to engineer out of your application so that it will scale. As we move to the cloud with containers and we're trying to elastically grow things, these are the things that are going to prevent you from doing that. You will never see these patterns, even with the best 1 second line chart data. So again, aliasing is everywhere. It's in all of these industries that we know and we love and we trust and we demand more from and more fidelity from, yet relatively, as a whole, lacking from the monitoring space. Big data is that solution. And what I want you to do is walk away with this question of, how good is good enough? If you have 60-second data, what can you do with it? You could do course trending, you can do reporting. If you want to be able to determine, if you're overall, on average, are your VMs running hot in the cloud, this is fine, not a problem. If you've got 15-second data, you're going to be able to detect longer chronic types of events. Things that when they go bad for minutes or hours. 15-second is great at that. It will help you detect it. May not help you troubleshoot it too much because then again, it's tough to correlate the difference in the the cases. But it depends on the nature of the problem. And again, it's like the example. What do you need to detect the level of water in a pool? You don't need a lot of coarseness. What do you need to detect the light level in a room? You've got to be very, very quick in that. 1 second data is going to help you catch, detect, troubleshoot these intermittent micro issues, right? So we think about these microbursts, and this is what I see the whole world is about now. When we're talking about containers and a lot of shared resources, you just get these moments in time where a lot of containers are all making the same demand at the same time, and for a second, that machine gets crippled and goes to its knees. And response time goes up, and then a second later, everything is fine. Right? So most of the things I'm being tasked with fixing for my customers, are these types of intermittent types of problems. You need a very fine view to catch those. And if you really want to catch the complex, multidimensional issues that go across tiers, when certain servers under certain circumstances, under certain workloads from certain users are having problems, big data is the only way you're going to be able to even know that those issues are existing. Okay? So hopefully, you guys have had an eye-opening experience here. I'm going to ask you, I'm just very curious because this is somewhat of an esoteric TED Talk. What did you think of the session in 3 words? And while you guys are kind of submitting a little bit of feedback, do we have any questions? I've got a couple more minutes. Anyone awake? Okay, question? No. Is anyone submitting words? Is it not refreshing? You guys just want to go? Oh, helpful. Outstanding. I'm glad that's the first word. I was really afraid you're going to say something, mean. So if you have any more questions, I'll be at our booth 313, I believe, for the rest of the day. I'd love to have questions about, sort of scenarios you've seen, whether or not, I think we could have measured it differently. I love, this is what I live and breathe, is trying to solve these squirrely problems and trying to fix the things that other people were not able to do. So in closing, please, like I said, come visit us. If you want to follow me on the web, here are the various links. Like I said, YouTube videos, that's my short link, JH-YT. I've got some other cool related sessions. Performance Phantoms are one you'd probably like. It's a lot of fun, especially when it comes to virtualization and the problems that can happen with contention. And that true plot is me. It's not faked. I didn't Photoshop it. I just figured out how to generate end user experience data in a way that happens to coincidentally look like this. And as a line chart, I don't look like that. Some of you might think it's better as a line chart, but I don't know. So with that, thank you. We came in right under time. I appreciate your attendance, and please enjoy the rest of the show.